Hello students, good evening. Welcome to Wallah. My name is 𝐂𝐚𝐿. We are discussing theory of computation lecture series for GATE 2025 point of view. So today is our lecture number 10. In our previous lectures, we discussed some of the concepts related to finite automata and regular languages. So we completed all the concepts of finite automata, deterministic finite automata, non-deterministic finite automata, regular language detection, regular expressions. These topics are already completed. So today our discussion is on grammar. In the previous class, we started some concepts related to grammar. Today is our part 2 on grammar. So grammar is one of the very important topic for computer science because it is a common subject for compiler design, theory of computation for both of this. So some of the topics related to grammar we studied already. Today we will continue some more advanced concepts on grammar. How this grammar is useful, how grammar is important for compiler design, and what are the types of grammars. There are various grammars exist here in theory of computation. What are the different types of grammars exist? All these things we are going to study in today's session. Right. Before going to start this, what we studied in the previous session, just let me give a recap of that. So in the last class, we studied what is grammar, definition of the grammar. We have seen what is derivation and sentential form. Sentential form is not covered in the previous session. Mostly we will see in the today's session. So what is grammar here? In our last session, we studied the definition of grammar like this. Grammar is nothing but set of rules of a language. So whenever you say language, I have given the example of so many languages in the last class. English language, English grammar. So students will study so many years for English grammar. English language, English grammar. Hindi language, Hindi grammar. Any language, its grammar exists. Like this, computer science is full of languages. C language, C++, Java, so many languages. If you have these many languages, for every language, grammar should exist. What is a grammar? Rules of that language. Every language having particular rules. Those rules called as grammar. Set of rules used to describe strings of a language. Set of rules used to describe strings of a language, known as grammar. The set of rules is called as grammar. So how generally grammars will be represented in computer science is the help of 4 tuple notation. 4 tuple. Non-terminals, there exist non-terminals are also called as variables. Non-terminals, variables. Then terminals. Number of productions, starting symbol. So if I have a grammar of this kind, this is one of the grammar. If you have any grammar of this kind, then what type of NTPS analysis we can perform on this? How many non-terminals? In general, non-terminals are nothing but capital letters. That's why non-terminals or variables is, we performed this analysis even in the last class. So in today's class, generally computer science grammars looks like this. The grammars of computer science looks in this way. Non-terminals. So non-terminals here are nothing but S, A, B. In general, small letters are comes under terminals. So terminals are nothing but whatever exists in the first one, first symbol of the grammar, that is starting symbol. Here starting symbol is nothing but S. Number of productions, arrows 1, 2, 3, 4. Total number of productions are 4. So like this, every grammar is having this 4 tuple, 4 things: variables, terminals, productions, starting symbol. Every grammar, C language grammar, you say these things. So the grammars of computer science, C, C++, Java, these languages, grammars, how they exist is in the form of NTPS notation. We can frame by using NTPS notation. Right. So then we have studied derivation. So if any grammar exists, whenever you say grammar exists, grammar generates, definitely there is a equivalence between language and grammar. So if you have a grammar, for this, language exists. There is a grammar language equivalence here. So for every grammar, language exists. Every language, grammar exists. This is the equivalence. So whenever grammar is given, how to identify language of that? For that purpose, we will use derivation. We'll try to generate strings from the grammar. That is called as derivation. So the process of deriving strings. The process of deriving strings from given grammar known as derivation. This derivation is of 2 types. We can perform while doing derivation. Leftmost derivation we can perform, rightmost derivation we can perform. The leftmost derivation or rightmost derivation. And one more way is there, tree representation, graphical representation of derivation, that is called as parse tree or derivation tree. This definition also we studied. Derivation tree. A tree representation of a derivation, graphical representation of a derivation. The derivation is generally looks in this way. The graphical representation of derivation is known as derivation tree or parse tree. Right. These parse trees are most commonly used in compilers. Compiler design time, generally we use this type of derivations. Right. Today, in today's session, we'll see grammars, how these derivations will be performed on grammars. How we construct derivation tree. Construction of derivation tree is one of the major thing. So whenever we take any example grammar, how to construct the derivation tree for that, and how to analyze what is the language and all this from the grammar. So different type of questions possibility from grammar, how it will come. Those things we are going to study in today's session for gate point of view, especially for gate point of view, right? So just before going to start that, leftmost derivation, what is that leftmost derivation here? Whenever we are doing derivation, replacement, derivation is nothing but replacement of non-terminals by left hand side part by its right hand side part. That is called as derivation. It is a derivation in which leftmost non-terminal is replaced. Leftmost non-terminal is replaced by its right side at every step. Our right hand side part at every step is called as leftmost derivation. Rightmost derivation is, it is a derivation in which rightmost non-terminal is replaced. I'll explain all this while doing derivation. Rightmost non-terminal is replaced is called as rightmost derivation. Which derivation, whenever we are deriving the string, which derivation we have to use? Either leftmost derivation or rightmost derivation. For that, there is no conclusion, that is completely depends on you. Actually, whenever we are doing compilers, construction of compilers, some parsing algorithms like top-down parsers, they use leftmost derivation. LL1 parser or any parsing top-down parsers uses leftmost derivation, whereas some parsers like bottom-up parsers, they use rightmost derivation, not exactly in reverse order. So this is what depends on our requirement. Sometimes we can use leftmost derivation, sometimes we can use rightmost derivation. We cannot say exactly this is what required for our procedure. That is completely depends on our requirement. We cannot say only this is good, this is bad, like this. There is no way of asking questions. Right. Now let us see in today's session all these things we studied in the previous class. Today we'll try to apply derivation trees. We'll try to generate the strings from the given language, or we'll try to generate strings from the given grammar. So language to grammar, that we'll see later. Grammar to language, right? So this is one of the grammar we generally have. Here there is only one non-terminal, only one starting symbol is only one, and number of predictions are T, and A, B are the terminals. NTPS analysis on this. Now the thing is, what is every grammar, the moment we look at the grammar, if you are a GATE aspirant, if you are preparing for GATE, the moment you look at the grammar, you have to think in mind what is the language of that. So grammar is nothing but a language. So what is the language of this grammar? Those things we have to get in mind immediately, right? Now this grammar definitely produces some language. It is definitely producing some language. What is that language? We need to analyze that. Okay, now we'll perform a derivation. I'll write all the strings. There is no direct way here. We'll try to generate some strings, then we'll generalize that. Let us generate some strings, then we'll generalize. First one, see the derivation here. Start from starting symbol, S directly producing epsilon from this production. So epsilon is generated. Then take this one, S gives AS, and then we are replacing this. Derivation, I am doing this tree structure is called as derivation. This is derivation. Trying to generate the strings is called as derivation. So A is generated here. Then if I take this production, I can do like this. S is replaced by AS. Again this S can be replaced by any number of times AS. S can be replaced by AS. This one. Again S can be replaced by AS. Again S can be replaced by epsilon. If I do like this, 2S will be generated. 3S will be generated. Any number of S will be generated. This is one possibility. Then if I expand this, S gives BS. S replaced by epsilon. 1B, again BS. 2B's, epsilon. 3B's, any number of B's. Then if S is replaced by AS, S is replaced by BS, then epsilon, AB generated. S is replaced by BS, S is replaced by AS, epsilon. If I generate in this way, then BA generated. So like this, the type of strings generated by this grammar is A plus B whole star. A plus B whole star. So many tree structures. This is generating infinite number of strings. This grammar generates infinite language, infinite number of strings. We need not to wait till infinite time. Need not to wait for infinite time. So what we have to do, we'll generate some strings, we'll generalize. There are so many recursive things are there, so we'll generate something and we'll generalize. So like this, if you do, we can construct strings for so many grammars. So these are the parse trees. These are called as derivation trees. This procedure is called as derivation. Derivation. Right. So for this grammar, what is the question? Identify language generated by following grammar. For this grammar, the language is nothing but complete language, A plus B whole star. That is sigma star language it is generating. Generating sigma star. That is the answer for this. Right. I think it is easy, just it requires only practice. You just need to do practice. There is nothing more than that. We have one more grammar here. Now, what is the language of this? Identify the language of this grammar. Identify the language equal to this grammar. Same thing, we need to perform derivation. First epsilon, S replaced by epsilon, then S is replaced by ASB, replace it by epsilon, then it is producing AB. So S is replaced by ASB, S replaced by ASB, then S is replaced by epsilon. Then the string which is all the leaf nodes, our string is nothing but all the leaf nodes is called as our string. So whenever you read all the leaf nodes, this is the string which is generated here. This is the way. Similarly, take it recursively 2 times. S is replaced by ASB. Again S is replaced by ASB, replaced by epsilon. Now what happens? If you read all the leaf node strings, then 2A's, 2B's. Type of string generated here is A's, B's equality. Number of A's and number of B's are equal. Similarly, if I go for this, S is replaced by ASB, S is replaced by ASB, S is replaced by ASB, epsilon. 3A's, 3B's. Like this, number of A's and number of B's are equal here. So the language for this is nothing but A power n, B power n, n greater than or equal to 0. Here also we can read the leaf nodes. All the leaf nodes is called as yield, actually, yield of the parse tree. This yield gives us, read this from left to right. Leaf nodes, if you read from left to right, then we'll get our actual string. So like this, generate first epsilon is generated, 1A, 1B generated, 2A's, 2B's generated, 3A's, 3B's. Like this, if I generalize, number of A's and number of B's equal type of strings are coming. So directly I am writing language as A power n, B power n greater than or equal to 0. What is the actual, somebody asking, sir, what is the actual use of this language in real life? I told you, I think you joined late. To design compilers, compiler design, one of the practical example. If you want to design compiler, what is a compiler? It is checking your language is correct or not. So to check your language is correct or not, it should know the rules first. How we will provide rules to the compiler? In the form of grammars. So grammars are nothing but our rules of a language. So rules of language we are representing, we are showing in a simple way. That is generally grammar. So grammar is like small set of notation, that is a NTPS, non-terminal terminal production starting symbol notation. By using that notation we are representing. So this is what is the way of generation of strings, guys. Whenever a grammar is given, if you want to generate the strings, the best thing is parse tree, derivation trees. These derivation trees are the most important things in our grammar. If you want to do anything in grammar, the only way is use derivation trees. generate some strings using derivation trees. Using derivation trees, generate some strings. Based on those strings, we'll generalize the language. So now we have seen for 2 examples. If a grammar is given, identification of language from the grammar. So here we identified, we concluded language by using derivation trees. Here also for this grammar, we constructed some of the derivation trees and then we identified the language equal to this. Right? Let us see one more thing. What is the language for this grammar? Every grammar, whenever you say grammar, grammar is equal to one language. Every grammar is generating one language. What is that language? Language is nothing but set of strings. It is generating some kind of strings. What kind of strings it is generating? Those things we have to see here. Okay. Right. First, let us start from here. There are so many things are there involved here. This is generating infinite number of strings. So let us try to analyze every non-terminal what type of strings it is producing. So come to the non-terminal A first. Non-terminal A. Non-terminal A, what type of strings it is generating? A, capital A. Whenever you take this production, A, small a followed by capital A. This capital A replaced by this production. Again this we can replace. Again this we can replace. And so on. If I go, it is producing number of A's recursively. So I can say the language generated by this will be A power n. Am I right? Instead of A power n, you can, if you want to show in regular expression structure, this is nothing but A positive closure, A plus. A plus, positive closure. Right. Now come to this production. S gives ASB. What type of string this production generates? If you observe the derivation tree of this, observe the derivation tree of this one, this production. Left hand side is, right hand side B is equal. So this production will give us A's and B's are equal. So based on this, we can able to generate A power n, B power n. But there is some small problem with this production. We have a problem with this production. What is that? We never generate string from this. See here, S is replaced by ASB. Again S is replaced by ASB. Again S is replaced by ASB. So this is the way it is going on. So if you want to end this somewhere, you have to include capital A. So till now what happened? So the use of this one will be A power n, B power n. In the middle, at least one time you have to use capital A. Whenever you use capital A, this is mathematics, simple mathematics equations. A power n, B power n. Capital A is nothing but A plus. A plus. This is the language. How this language looks like? A power n, B power n is going on, equality is going on. Whenever I want to replace capital A plus. That means number of A's are becoming more than number of B's. So here the language is nothing but A power n, B power m, n definitely greater than m. N definitely greater than m. N comma m greater than or equal to 1. 1 onwards. Is it clear? So like this, if we construct a derivation trees, we can generalize variables, generated type of strings, how one variable is producing what kind of strings. If you generalize this, then it is easy for us. Is it clear? So like this. If any grammar is given, we solved mostly 3 examples. If a grammar is given, produce parse trees, apply derivation, identify what kind of strings are generating. Based on that, based on the type of strings generated, we have to produce the language of that. We will generate some strings, we will generalize. If we generalize, we will get the exact language of that grammar. This is the way. Right. Now we will go for reverse of this in a similar way. If language is given, sometimes they will give language, how to construct the grammar from this language. Here in this example, he has given a grammar for us. Sorry, language for us. He has given a language. We need to construct a grammar. So, by using NTPS notation, whatever the rules of this language is there, show those rules. This is where exactly application of grammar will be visible for you. Where grammars, how the grammars will be useful for us. So we will take some languages. These are called as formal languages. Same thing we can apply for general language, C, C++. For that also we can apply. So take any language, how the rules of those language exist. For those rules, you write NTPS notation. So here what is this? Number of A's followed by number of B's. This is nothing but number of A's followed by number of B's. So A's you generate recursively, B's you generate recursively, one followed by other. So for this, capital E I am taking a non-terminal. This non-terminal I am using for generating number of A's recursively. Starting from 1, so minimum string is A. A is generating, whenever I apply recursion like this recursion will generate A infinite number of times. If you want to generate anything infinite number of times, we need to use a recursion here. So this is generating A infinite number of times. Similarly, B is recursively, that is recursion on B, starting from 0 time epsilon at S, A followed by B. This is the grammar equal to this. So this is nothing but our A power n. This is nothing but our B power m. A is A power n followed by B power m. That's all. So in this, if we want to perform NTPS analysis, how many non-terminals? Non-terminals of this grammar, 3 non-terminals, S, A, B. How many terminals? Small letters A comma B. Small a, small b. Number of productions, okay. Starting symbol is S. How many productions exist in this grammar? See this, whenever this or symbol, or is given, then this side one production, this side one production, two productions we have to count here. So for this, one production, 2, 3, 4, 5. So total number of productions are nothing but 6. So this is the total NTPS analysis on this grammar. So if for a language A power n, B power m, the equivalent grammar is this one, and the total non-terminals, terminals, production, starting symbol information is this one. So grammars we constructed. If grammars are given, language we generated. This is the way. For this, if grammar is given, for the language, derivation concept. If language is given, construction is somewhat initially it looks like complex thing, but after some time you can construct easily. And one more thing is, whatever I am constructing here, your answer need not be same, not necessarily be same. For one language, different grammars exist. There can be so many grammars, so it is need not be always one. That's why whenever a language is given, I can construct something differently, you can construct something differently. All of these can be valid, they can be equal, so not a problem. There is no minimization grammar concept here, so we can construct grammars properly. Only thing is, you should not construct a wrong grammar. In a different way you can construct, that is not a problem, right? Okay guys, this is the way of construction of grammars. So grammar constructions, language to, grammar to language generation. Then we see types of grammars. We are constructing grammar, but here we have 4 type of grammars in our total in our computer science. We have a regular grammar. Computer science is all about 4 things: regular, context free, context sensitive, recursive enumerable. I think we have this diagram somewhere here. Wait. This is our theory of computation diagram. Somebody asking which is a tough subject in GATE computer science. If you read properly, nothing is tough. If you ask me, for me almost all are equal. Only thing is you have to practice more. Start your preparation initially, earlier. Don't start preparing hurry-burry in the month of December. That is not the right way. So if you start preparing from now onwards, then understand every subject thoroughly, then everything will be easy. See, nowadays it is online. You can watch subject n number of times, then practice. See here, reading book, understanding subject is the basic thing. That works only for 30%. Solving questions in a different way, thinking about the question in different way, that is a major thing here. 70% of your rank depends there. That's why for that the faculty help is required. So we will give you different varieties of questions, how to solve those questions differently. That is what I am explaining here. If you see, what I am not teaching whatever is there in the book. You can watch all my lectures. I am not teaching whatever is there in the book, because we are going for GATE preparation. What type of questions asking in GATE? GATE is full of questions only. So to attack those questions, to solve those questions, what should be our strategy? What should be our approach? Those things we are teaching here. If you learn that, every subject becomes easy. The only way is, the way of preparation should be in that path. Okay? Right. So here, this theory of computation is all about 4 things. Learning about 4 concepts: regular, language or regular, grammar. here I am saying grammar, regular grammar. Next, context free language or context free grammar. From first class onwards, we are observing this diagram. This is called as Chomsky hierarchy. Chomsky hierarchy. Oh, it's not uploaded. Part 1 is uploaded already. It is the last class. You can watch my last class recording. There, grammar part 1 is just a basics where we studied grammar in a basics way. So today's class is the actual one for grammar. Right. Chomsky is the person initially he introduced the rules for these grammars, 4 type of grammars. So type 0 grammar, type 1 grammar, type 2 grammar, type 3 grammar. Like this 4 grammars he classified. So based on the rules of the Chomsky produced the rules for these 4 types of grammar. Chomsky classified grammars into 4 categories. He named it as type 0, type 1, type 2, type 3. Then afterwards, if you frame the relation between these rules, the relation is coming like this. Type 3 is subclass 2, type 2, type 2 is subclass 2, type 1 is subclass 2, type 0. And this type 3 comes as our regular grammar, type 2 comes as our context free grammar, type 1 comes as our context sensitive grammar, and type 0 comes as recursive enumerable grammar. Like this classification is initially given by a person called as Chomsky. He is the initial person who has given the classification on these grammars. So theory of computation is finally this one. Learning about all these 4 things. 4 grammars, 4 languages, 4 automata. Total theory of computation is first class to last class what we are studying, whatever given by Chomsky. So 4 grammars, 4 languages, 4 automata. Now today's is our grammar session. So we'll focus our concept to grammar. So here also we are constructing grammars. Previously we constructed grammar. After constructing grammar, your grammar falls under which category? That means after designing a grammar, I told you to construct a compiler, to design a compiler. First, we have to give grammars. We have to design grammars. Grammar we have to design. After designing grammar, we have to know what the grammar comes under which of this type. Which one? Either it is regular grammar, or context free grammar, or context sensitive grammar, or unrestricted grammar. That information we have to gather. Once you confirm that it is particular grammar, corresponding automata we have to construct them. Assume it is a context free grammar. Then the suitable automata, if it is here, the suitable automata is push down automata. Finite automata not suitable. If your constructed grammar is type 0 grammar, then finite automata fails, push down automata fails, LBA fails. Turing machine we have to construct. Like this, once we fix about the grammar, we fix the grammar type, we identify the grammar type, then we will talk about automata concept, we will talk about language concept. This whole picture is baki hai, abhi. Right. So now let us see how to identify the coming grammar. See, previously I think I have constructed one grammar. Assume this is the grammar. This is the grammar. What grammar it is? Regular grammar, context free grammar, context sensitive grammar, what is that? That information required for us. This is the, assume this is the grammar. Can anyone tell me what is the grammar, name of this grammar? What is the name of this grammar? If anybody give me correct answer, I'll give some gift. This is very important one. What is the name of this? Regular grammar, context free grammar, context sensitive grammar, unrestricted grammar. Right. Let us study these rules first. See, here also I have constructed a grammar. What is this grammar? The beautiful thing here is this language is regular. This language is regular, but this grammar is not regular. This is context free. Language is regular, grammar is not regular. Why it is happening? All these things we'll study. For this, you should know the rules first. These are the rules. All grammars, so let us try to understand these rules. There are 4 grammars here: regular grammar, context free grammar, context sensitive grammar, unrestricted grammar. If you are a GATE aspirant, serious GATE aspirant of computer science, without this concept, don't write GATE. Grammar is a minimum thing. There is no GATE paper without grammar concept. It is common for 2 subjects, no? 2 or 3 subjects. Even for programming language, somewhere also we will see these grammars. Okay, right. So, let me start from unrestricted grammar onwards. See, generally, all grammars is of the form alpha tends to beta, this format. All grammars is of the form alpha tends to beta. Means, there is an arrow, left hand side something is there, right hand something is there. So, LHS contains something, right, RHS contains something. There is arrow in the middle. General grammar structure. This is the general grammar structure. Right. What is alpha here? Alpha can be any number of terminals and non-terminals. Beta can be any number of terminals and non-terminals. So, alpha can be any number of terminals, non-terminals. Beta can be any number of terminals, any number of non-terminals. Right. How this regular grammar looks like? Unrestricted grammar. Left hand side you can take any number of non-terminals, terminals. Right hand side you can take any number of non-terminals, terminals. That is called as unrestricted grammar. But there is one common rule for all this. Alpha should contain at least one non-terminal. Left hand side part, for all grammar this is a common rule. Left hand side part should contain at least one non-terminal. That is a common rule for this. What is the unrestricted grammar? So, left hand side can be anything, right hand side can be anything. Also called as type 0 grammar. Type 0 grammar. This is the rule. Right. Next, type 0 grammar, unrestricted grammar. Rule is this way. The suitable machine for this is Turing machine. The rule is clear for this. You can add anything in the left hand side. I can show you some of example of this grammar for type 0. This is one of such grammar. Left hand side non-terminals, terminals allowed. Right hand side non-terminals, terminals allowed. Any number of non-terminals, terminals in the left side, any number of terminals or non-terminals in the right side. Such type of grammars are called as type 0 grammars. Type 1 grammar. What is the type 1 grammar? Type 1 grammar, also called as context sensitive grammar. Its rule is like this. Same, almost type 0, type 1 looks like same. Left hand side alpha, right hand side beta. Left hand side any number of non-terminals and terminals allowed. Right hand side any number of terminals and non-terminals allowed. But the thing here is beta value should be greater than or equal to alpha value. This is the condition here. That means length of the right hand side always greater than or equal to length of the left hand side. Length of the right hand side always greater than or equal to length of the left hand side. That is what meaning of this. So right side should be greater or equal than left side. It should not be lesser than left side. That is the rule here. Based on this, we can see this example. Is it a valid type 1 grammar? Left hand side length is 2. Right hand side length is 1. This is not type 1. This comes under strictly type 0. That is the meaning here. So in type 1, right should be always greater or equal. It should not be lesser. That is right. Then we move to next rule. Type 2. Context free grammar. Context free grammar. Context free grammar is left hand side only non-terminal. Alpha is nothing but alpha belongs to any number of terminals or non-terminals whole star. Here actually alpha beta belongs to like this only. Alpha belongs to any number of terminals, any number of non-terminals whole star. Right side can be anything. There is a restriction on the left side only. There is a left side restriction. What is that restriction? Left hand side should always be one non-terminal. Only one non-terminal allowed. Right side anything. So left side one thing, right side anything is context free grammar or type 2 grammar. Right. Let us come to the regular grammar. Regular grammar. What is the regular grammar here? Regular grammar also there is a one rule, common rule between type 3 grammar, type 2 grammar. That is, in context free grammars and regular grammars, left hand side only one non-terminal. Left hand side only one non-terminal. Right hand side anything is context free. If you make restriction on right hand side also, that comes under regular grammar. What is the restriction? See the right side. Left side only one in regular. Left side, the non-terminal is only one allowed. In regular grammars, let me explain separately here. This is somewhat very important. For regular grammar, the structure will be this way. So this type of structure left hand side only one, right hand side also at most one non-terminal. The maximum allowable non-terminals in the right side is at most one, maximum one, otherwise zero. Non-terminals present in the right side. This is regular grammar structure. Whatever the at most one non-terminal present in right side, if it is present in rightmost side, those type of things are called as right linear grammars. Right linear grammar. Whatever is present in the left side, that is called as left linear grammar. If non-terminal present in leftmost side, that is comes under left linear grammar. Like this, your regular grammars are of two types: right linear grammars, left linear grammars. So regular grammar is nothing but left side one thing, one non-terminal, right side at most one non-terminal. If this at most one non-terminal present in rightmost side, that is called as right linear grammar. At most one present in leftmost side, that is called as left linear grammar. So like this, we have left linear grammars and we have right linear grammars. So right linear grammar as well as left linear grammar. Right? So this is the way. And see here, one more important thing is, if you want to say grammar is regular, it should be either left linear or right linear. Mixing of both is not allowed. A grammar is completely right linear is regular, completely left linear is regular. If both are there, then it is not regular. This is the very important point here. This is about complete structure of the regular grammar. So this is regular grammar. Regular grammar. Then this is context free grammar. The rule of context free: left side one thing, right side any number of non-terminals, any number of terminals. Context sensitive grammar: left side, right side, anything, but length of the right hand side should be greater than or equal to length of the left hand side. Length means number of terminals and non-terminals in the right side always greater than or equal to number of terminals and non-terminals in the left hand side. Then we have unrestricted grammar. Unrestricted grammar is nothing but alpha gives beta format. Here left side can be anything, right side can be anything. See, there are restrictions in the previous thing. Here right side length greater than or equal, restriction. Here left hand side only one restriction. Here left side, right side restriction. But here no restriction. Left side can be anything, right side can be anything. That is called as unrestricted grammar or type 0 grammar. So like this, we have 4 type of grammars. So remember these rules. Now the moment we look at any grammar, after constructing grammar, this grammar falls under which category? Regular or context free, those things we have to decide. So based on these rules, let us try to analyze for some of the example grammars. And we identified the corresponding, if the grammar is regular, corresponding automata, finite automata. Grammar is context free, push down automata. Context sensitive, linear bounded automata. Unrestricted, Turing machine. Corresponding automata also exist here. So this is the overall structure of the grammar. Based on these rules, if you apply, then we can get Chomsky hierarchy. Right. Now let us try to analyze some of the grammars here. This is one of the grammar. What is the name of this grammar? what name you can give to this grammar? Is it regular grammar, context free grammar, context sensitive grammar, unrestricted grammar? So let us start from first type 3 onwards. Type 3 onwards, because in the Chomsky hierarchy this is there in the lower part. So if not 3, it can be 2. So what is type 3 regular grammar? Regular grammar should be of this type. It should fall under this type, or it should fall under this type. Either it should be a left linear or it should be a right linear. But what is this example, our given example? This production is right in this non-terminal exists in the rightmost side. So this comes under right linear. In this non-terminal exists in the leftmost side. This comes under left linear. So left linear, right linear, both exist in this. Is it allowed for regular grammar? Is it allowed for regular grammar? No, not at all. Regular grammar means either it should be completely left linear or it should be completely right linear. Mixing of both is not allowed. So this is not regular. This is linear, but not regular. If not regular, then we have to check for, see, this is the way we have to check. First check for type 3, then type 2, type 1, type 0. First check for 3. We have concluded that this is not comes under type 3. If it is not comes under type 3, then check for type 2. What about type 2 here? Left hand side only one thing, right hand side anything is allowed. So here the rule satisfies. The rule actually matches here. So this is comes clearly under context free grammar. Context free grammar. So this grammar is, many students the moment they see this one, they may think this is a regular grammar, but this is a context free grammar. Context free but not regular. Right. Let us try to analyze one more. This is one more grammar. Give name of this. Either it is regular grammar, context free grammar, context sensitive, what. So this procedure always you have to start from 3 onwards. Check for 3, then 2, then 1, then 0. Right. So what is type 3? Left hand side one non-terminal, right hand side at the max one non-terminal. But the moment you see two non-terminals in the right side, type 3 fails. Type 3 fails. Then let us check for type 2. What is type 2? Left hand side one non-terminal, right side anything right side allowed. So this is once again comes under context free grammar. once again comes under context free grammar. Right. Check, verify for this. What is the give name for this grammar? Type 3, type 2, type 1, type 0. Start from type 3 onwards. So to say, look at this. Whenever left hand side, if you observe more than this, left hand side more than one non-terminal or terminal non-terminal together, more than one length exists. Type 3 fails, type 2 fails. Because in type 3 left side only one, type 2 left side only one. Whenever this is there, we can rule out these two types. It is not type 3, it is not type 2. It can be type 1 or type 0. What is the type 1? Length of the left hand side, we have right hand side we have to calculate. Length of the right hand side should be greater than left side or equal with left side. Length means 2 here, 1 here. Length is 2 here, 2 here, equal. Whenever length of the left hand side becomes greater, what is that rule? It is clearly violation of type 1. So in the type 1, left side should be equal or lesser. Right side should be greater or equal. But here what happened? Right side becomes lesser. 3 also fails. So this is type 0. So the name for this is unrestricted grammar. Name of this grammar is unrestricted grammar. So it falls under the category of unrestricted grammar. Okay, like this. So whenever grammars are constructed, we have to give this grammar comes under which rule, whether it comes under unrestricted grammar or it comes under context free or it comes under a type 0, because the suitable automata we have to bring into picture. Once you decide this, what is the automata of that? That one also we need to identify. Okay, right. So this is about the construction of grammars and then identifying the types of the grammars. Okay, that's all about grammar session, about detection, construction, identification of type of grammars and grammar to language generation. Okay, that's all about today's session, guys. Thank you, students. See you in tomorrow's session at the same time. Thank you. Bye bye.